How's it going? This is Qasim, and today I'll like to demonstrate um, a project I was working on over the past couple of days. It's a project related to BCI, or brain computer interface, as you can see the wearable device on my head, and BCI basically all it does is acts as a receiver between your brain and transmits the signals, which I'll get into in a bit. Transmits those signals to an ICU, a programmable chip, or a computer program, etc. And so, what signals does it actually send? Well, it really depends on the type of BCI that you have, but the one that I have sends electrical impulses, or the change in electric potential at the scalp or the surface of your brain. As you can see, I have five, or you can't really see, but I have five electrodes or five channel sensor, and they're each located in three different regions of the brain. Two of them are in my temporal region, one of them is in my parietal, and two other are in my frontal regions of the brain. And the purpose is to measure the changes in the electric potential over a function of time. So the data is it's in real time, that emotive, the BCI that I've purchased this device from, and it's in real time, and it's all in the time domain, and it's up to the engineer to convert it from time to frequency, as they like, using DSP algorithms and tools. But let me show you guys some of the cool stuff that you can see from this BCI. And as you can see in here, you can see the changes in the potential at the scalp region of my brain over time. And there's a lot of noise obviously associated with it. But it does have a filter bank. I believe they use a two cascade port, or two port cascading filter of high pass filters to eliminate DC noise. But I guess there's also a little bit more noise due to the fact that there's very less charge left in the headset, as I've been using it over the day. Yeah, it has a lot of noise. So here's what I'm gonna do. So the program that I built takes in the data that is transmitted from my neural signals, and based on the data that my brain feeds into, embeds into the program, it can figure out what I was thinking about. Not like science fiction level stuff, but what it does is it has been programmed in a way where, given a certain thought, which I'll come into later, it can it can perform arithmetic operations based on my thoughts. So right now, the application of my BCI device um, is strictly limited to calculations, numerical calculations. Suppose I wanted to perform 21 times 34, right? I can do it on the standard calculator, or I could just think about the number two, the number one, the operation, multiplication, and then B, or the second operand, being 3 and 4, and it would automatically compute or solve that. And that's pretty cool. And there's a way to do that, and that is this device, and that is what this program that I've designed can do. All you have to do is think about the individual numbers, and I'll show you how I think about it. And based on that data that I feed into the network, it figures out what I was thinking about, and based on that, it decodes it into numbers and performs the various operation or the desired operation. And lo and behold, that's my output. So without further ado, let's get started. Let's do something easy and fast, because I don't think this headset's going to last for long without having to recharge it. So let's just do something simple. Let's do 6 plus 3. I think that's 6 plus 3. All the 3 Tesla numbers. Good old math joke. So let's say first number, right? Let's do 1 test, and since I'm the subject, I'll just put my name in. I highly doubt it's going to work because data is there's a lot of noise, ton of noise due to the fact that there's very few charts. There's a lot of, it's almost completely drained. So, but let's still give it a try. Okay. So that was the number 2, and oh wait, I thought about the wrong number. 9. Yep. I was supposed to think about the number 3. I actually thought about the number 2. All right, let's do it again. So that was the first number that I thought about, which was 3. Now I have to think about 6. Well, no, sorry. Now I have to think about the operation. So plus. All right, that worked. Now finally, the third data point or data is the op B, which is 6. And that is it. And I believe I am done. So these are my 3 files. And I'm just going to export it. So it's not fully real time as of now. This is a working prototype. But I eventually get to be all real time based protocol. And let's just run it and just see what our program outputs. Um, let's see, yeah, it goes in the right. I'll run the Jupyter Notebook simultaneously such that you can see their matplotlib plots. Or it already worked, I guess. Okay. So this is the data for file number 1. As you can see, it's the sample rate is a 7-bit, so it's 120 samples per second. It prevents. I think with the given data that I have, it prevents aliasing, which is established through the Nyquist frequency or the Nyquist-Shannon theorem, and yep. And you can, so this is data in the time domain, and I would just have to perform a DFT Fourier analysis, and you could do that using a fast Fourier transformation to convert it all into the frequency domain. The window that I would use would be regular Hamming window. So these are just different. So they're different channels of the brain. So there are 5 channels for the sensor, and each channel has its corresponding uh, time domain graph. So you would have 15 in total, since you have each op A is 1 unit that has 5 channels, so 5 graphs, plus has 5 channels, so does 6. And I'll just keep closing it. And let's see. Let's see what the program outputted. Oh wow. The program outputted 3 plus 6, and that is exactly what the objective was, 3 plus 6. And as you can see, the result is 9. It's quite beautiful. Yeah. This is the second time I tested it. And as you can see, it detected, based on the data that I was thinking about, based on some information that I was focusing on, it thought about, from that, it decoded it into numerical arithmetic expressions. And, as you can see, you have the operation here. So given, so now, how does it all do it? Well, I would have to tell you this. I treated noise differently than other engineers would treat noise regarding this sort of application. You see, muscle fluctuations actually change the neural activity, especially regarding the anterior of the brain. You see, so when I'm clenching my jaws, what's happening is as I'm clenching my jaws, I'm inducing a sudden change in flow of current across the scalp, which creates a sudden change in the peak frequencies of the potential difference at the scalp of my brain, which is reflected by all of these 5 electrodes. And it occurred to me while I was working on a different application of this. I have tested 7 hypotheses over the course of 6.5 days, and one of them was regarding whether our brains completely harmonize to a certain degree, obviously, because high gamma waves is only up to 50 hertz, whereas standard music files can go up to 440 hertz, which is, I believe, the A major. I'm not totally sure, but the point is, The hypothesis was whether our brains can predict, or whether we can predict a given a brainwave data file, can we predict what music I would be listening to or I'm listening to? And while I was testing it, I observed myself listening to certain genres of music, certain instruments, and I tried finding similarities with the corresponding music file. So obviously all of this was converted into the frequency domain such that we could extract some meaningful information. And the best estimator was not the music file itself. So if you ran like a basic similarity ratio test, let's say Jacquard similarity, it didn't, with respect to a music file versus the associated BCI data, there wasn't a very high correlation between, whether this file is similar to this. So I tried Euclidean distance, Manhattan, Jacquards, and cosine similarity. Cosine similarity obviously seems like a disaster for, not really a disaster, but not the best sort of approach. But I tried it anyways, and I didn't use any sophisticated DL algorithms. I just went straight with basic information retrieval algorithms. And from what I found was that there wasn't a very high significance in similarities. Sure, the resonant frequency more or less affected from the original music file did change your your brainwave neural activity, but it didn't detect the continuous flow of frequency over time. So the spectrogram was more or less the same. The periogram, obviously in the frequency domain over was more or less the same. But here's a seller. When you compare a given music file, a music file's BCI data with the same BCI data on the same music file in another different interval of time, the two are highly similar. Now, you might say, isn't that obvious? If I'm listening to a pop song at time t equals 0, and I listen to it at time t equals 86,400 seconds, which is a day, shouldn't there be a high similarity? Well, obviously you would think so. But here's the thing, I have tested it on emotions, actual emotions that we feel, like fear, love, happiness, etc. And turns out when I'm feeling something, let's say I'm feeling fear, and if I'm feeling fear at t equals 0 versus I'm feeling fear at t equals a day or 2 days, the two are very different. The thoughts, now here's it's important to point out that the thoughts are very different, right? But the emotions can more or less be the same, right? I could be afraid of a horror film, or I could be afraid of an intruder in my house. The two are different thoughts, but the feeling is the same. It's fear, right? So now the data that was collected regarding these different types of feelings should convey that regardless of the thoughts, if you have a similar emotion, your BCI, your brainwave data, your electrical signal, electrical activity should be the same. But that is not the case. That was the first hypothesis that I made, was regardless of the thought that you had, your brainwave data should more or less be the same. And I came up with this hypothesis after detecting that over a couple of 2 days. So this was over 2 days. The first day I tested myself watching a funny video on YouTube, so to reflect happiness. And the next day I tested myself through another hilarious video on YouTube from a comedian, and that I called it as happiness. And when I tested those two, they were highly correlated. As compared to something else, it wasn't as correlated with the other samples. So I thought um, that maybe there is a similarity between the meta of the feeling, so the emotion. If you go back, um, if you reverse a linked list, I guess. But that didn't turn out to be the case. So at the same time I was doing it, I clenched my jaw and I found this huge spike. And obviously that's noise, but I thought maybe I can use this noise for converting my application into a calculator that I initially started out with. And that is how I ended up with building a calculator app. So what does my application do? Well, it is a brain-computer interface that can solve any arithmetic, any basic, simple arithmetic operation that you think of. And it does it in almost real time. That is the application. And um, all the code is available on GitHub, and all the data that I've collected is stored on GitHub, and you can see it. It's here at Qasim/PCI, and yeah. So and this is the file that you use to run the program that you can see that was shared in the command. This is the main program for the calculator application. So I hope you guys enjoyed it. I hope you did. Make sure um, make sure you leave any comments, feedbacks if you have any. I'm definitely going to work on this a little bit more, or actually a lot more, to build further updates on the platform. And until then, let's keep hacking, and Happy New Year. Well,